Very well. In this lesson number 10, corresponding to the workshop assignment number 10, we want to talk about how to define interpolating functions. So we want to do interpolation. We want to use what's called a spline function. In general, what you have, sometimes you measure a set of data points. You have a discrete set of points of a physical quantity, okay? And let's say that you have this ordered from x0 to etc. to the nth value. So we have n plus 1 points. Correspondingly, you have y0, y1, and so forth. We want to be able to determine values between those measured points, for instance. Okay, so you want to make an interpolation. We can do that by doing a simple linear interpolation, which is very simple to do. Okay, just interpolate by a linear function between points. In this case, we would use something like this, polynomial, which has only two parameters, a and b, ax plus b, for instance. And it's very easy to determine the coefficients, the parameters a and b, given the coordinates of initial and final point. So we have one equation for this point here, for this pair of coordinates. We have another equation for this pair of coordinates. So we have two parameters, we have two equations. You can solve that problem easily. However, when you do this type of interpolation, the first derivative is discontinuous at these points. Okay? So this derivative has one value, the other one has a different value. So you don't have continuity of derivative. Sometimes it's important to have some information on the derivative. And in physical situations, these functions are smoother than they would be if we use the simple linear approximation. So in summary, if we use, for instance, linear, we can use a very simple interpolation just to calculate an estimate of a value between 2 points. You can use a linear interpolation using a linear polynomial a x plus b, a plus bx, let's say. If you want to make a continuous derivative, you can use a quadratic polynomial. Something like this, a plus bx plus c squared. Now we have more parameters, right? So we have to make sure that the function is continuous in each point of the grid, and also that the first derivative is continuous. So we're going to have something smoother. And if you want to really guarantee a more physical, let's say, curve, we would have a cubic polynomial. Now you have more parameters, okay? A plus bx plus cx squared plus dx cubed. Now you guarantee, using that, it's possible to determine the coefficient in such a way that not only the function is continuous in each point, but the first derivative and second derivatives are also continuous. So this is what we're going to talk about in this class, in this lesson. We're going to talk about a cubic spline. Let's talk about cubic splines. Let's consider that we have a set of data points. Let's talk about we are going to show how to solve the problem in one dependent, a single variable function. So I have this, n goes from 0 to n. So we have something like this, a graph with a set of points, increasing order. Okay, x goes from lower to higher value. So we have an open function. It doesn't mean that we cannot make closed function. We could do that too. I have to be careful with how we do it, but we can certainly do it. But let's talk about the open case. So we have x0, y0, x1, y1, and so forth until the last value, xn, capital N. Correspondingly, we have something like this, yn. In the intermediate value, we have x little n, lowercase n, corresponding height, yn. So we have xn plus 1. And here we have this height, yn plus 1. So I'm going to denote the cubic polynomial that goes from x0 to x1. I'm going to call the p0 polynomial. So the index is related to the starting value of x. This is going to be p1. Okay. And here is going to be the pn. It's going to be the pn polynomial. So you're going to write the pn in like this: pn of x equals to yn, the initial value, plus this would be the a coefficient. We're going to start from b. bn x minus x minus xn plus cn x minus xn squared plus dn x minus xn cubed. Now, notice that we can calculate, for instance, notice that Pn of xn, the way we did, is going to be simply yn, okay? The derivative, let's call Pn prime. Just going to point out some landmark values here. Let's call the derivative, is going to be Bn plus 2 times Cn x minus xn. But this is in xn is going to be 0, and the other term is going to be 0. So the first derivative is simply the coefficient, the linear coefficient. That's what we expected. And the second derivative, Pn2 prime, calculated at the starting value, is going to be 2 times Cn, and this term is going to be 3 times 2 times dn, then there's going to be a 0 value, calculated at the starting point. So these are important values. So what we have to do is to impose that each polynomial is continuous in each point. For instance, P0 at x1 equals to P1 at x1, and so forth. P1 at x2 equals to P2 at x2, and so forth. And we can impose that Pn at xn plus 1 equals to Pn at xn plus 1, of course. Pn at this point, xn plus 1 equals to yn plus 1. So we have a set of equations. We have n equations in the interior points, in all the points. In fact, notice that we have from 0, the last polynomial here, I didn't mention that, is the P n minus 1 polynomials. So you have n polynomials. So if we impose continuity, okay, in all those points, this one, and so forth, you're going to have if we impose that, sorry, come on. So if we impose that P0 at x1 equals to P1, you're going to have, until this last one, Pn minus 1 at xn equals yn, you're going to have n equations. Okay? You're going to have, notice that we have 1, 2, 3 times n unknowns to be determined. So n equations we can obtain by impose that Pn at xn plus 1 equals to yn plus 1. So for instance, if we pick Pn and calculate that xn plus 1 equals to yn plus 1, you're going to have something like this. Bn xn plus 1 minus xn plus cn xn plus 1 minus xn plus dn xn plus 1 minus xn plus yn equals to yn plus 1. You're going to have equals to yn plus 1 minus yn. This can be written in this way. I mean, let's call this delta xn, same value here. Let's call this delta yn. So you're going to have something like this, delta xn bn plus, sorry, this is supposed to be squared, this is supposed to be cubed, plus delta xn squared, cn plus delta xn cubed dn equals delta yn. So we have here n equations in this way. Recall that we need 3 n equations, okay? The next set of equation we can obtain now continuity of derivatives in the inner points, the interior points, okay? At x1, etc., until xn plus minus 1. So at this point, start from x1 until xn minus 1, we can establish that the derivatives are continuous, okay? Recall that we showed how to calculate the derivatives here. Here, for instance, is the derivative of Pn at xn, okay? Pn prime. So, for instance, we can say that P0 prime at x1 equals to P1 prime at x1, and so forth. So let's say that we can say that for instance, Pn prime at xn plus 1 equals to Pn. There's a wrong equation here. There's something above equation 6. There's a small typo there, so I have to fix it. So I can establish that Pn prime at xn plus 1 equals to Pn plus 1 prime at xn plus 1. We know how much this gives because we calculated here before, okay? You see that Pn prime at the same index is simply the coefficient. So this side here, we know how much it is. This is equals to Bn plus 1. This one is the derivative of the polynomial. Let's look at it. At xn plus 1 is going to be Bn plus Cn times 2 times the delta x plus 3 dn delta x squared. So we're going to have something like this, okay? Bn plus delta xn times 2 Cn plus 3 delta xn squared dn. Sorry. Yeah, this is correct. This is the derivative, right? Yeah. Equals to Bn plus 1. So, in other words, have an equation here. Now we have n minus 1 equations, okay? Here. Starting at n equals 0, 1, 2, until n minus, let's see, delta x, yeah, until n minus 2, n minus 2. So we have n minus 1 equations of this type, right? So we can proceed doing this, then we go to the second derivative. Okay, we're going to have something like this. With the second derivative, we're going to have also n minus 1 equation. We're going to have something like 2 delta xn, 2cn plus 6 delta xn dn equals to the second derivative. Recall that it's going to be 2cn plus 1. So this is going to be 2cn plus 1. So here also we have n minus 1 equation. It's just showing you have to work out all these equations by yourself to do how to do it. It's just outlining approximately how it's going to be. So far we have 3n minus 2 equations, okay? So let's focus on the case in which we have an open curve in which x0 is different from xn. So far we have 3n minus 2 equations. We just need 2 more equations. So far we have 3n minus 2 equations. Let's consider x0 different than xn. We can simply impose that the second derivative is 0. That's a simple boundary condition at the endpoints. Okay? So we say that P0, 2 primes of x0 equals 0, and Pn, 2 prime xn, Pn minus 1 at xn equals 0. So recall that this is going to give C0 equals 0, right? I mean, if you look at the derivative, look at the class notes here. I just put the polynomial here. That's how the polynomial looks like. Second derivative, this term is 0, is 2 times Cn. This term is linear, so the second derivative is simply 2 C0. Okay, so the equation we get is 2C0 equals 0, in fact. So it's the same as C0 equals 0. And if we go to n minus 1, we have the last term is going to be 2 times Cn minus 1 plus 6 dn minus 1 delta xn equals 0. That's what we get. Okay. So you're going to have something like this. 2 times Cn minus 1 plus 6 times delta Xn dn minus 1 equals 0. So that means something like this. So I have 2 additional equations. One is this one, this other is this one. So we have a full set of 3n equations to solve, and that can be solved in a very simple way, okay? So we have something, I mean, we end up with something like this. Let's consider the case in which you have different coefficients. These are equations 4, 6, 7, 8, and 9 of the class notes. So we have all of this. Here are the equations numbered from 0 to n minus 1. So we have all the equations that are required. Things get much simpler if we consider that the interval delta xn is always constant. In other words, the distance between successive points is constant. Then you can ask yourself, well, what if it is not constant? Well, I can tell you that you can implement a simple procedure to map the non-constant intervals into constant intervals. Then you can go back to inverse, to invert and calculate back for the original data set. Okay, so it's possible also to do for non-constant intervals. What you have to do is to implement for a constant interval and make a transformation to go back to your original data points. That's simple, not difficult to do. But let's focus on that condition. Let's assume that all the distances, delta xn, between successive points, the x-coordinate of successive points is constant. In other words, you're going to say that delta xn equals delta x. It's constant. Okay. So in that case, things get much simpler because now you can, you have all this. These are all the same. So, okay. So what we have to do is to call. You can make a new definition of parameters. You can call capital B a product delta x times b, lowercase b. Capital C delta x squared times the corresponding lowercase c, and d delta x cubed dn. So we have an equation, a set of equations of this type. Okay. So we have this set of equations. What we do here is to have a special case for C0 and Cn plus 1dn minus 1. So C0 is determined, okay? So I can, in these 2 equations here, we can express C and D as a function of B. Okay, that's what your guys are going to do. And we have a single equation for the B coefficients that can be cast into a matrix equation of this type here, which is the case we are focusing different endpoints. Okay. So that's the structure of the matrix equation. I have a 2, 1, the first row. All the other elements are 0. And we have a 1, 4, 1 that repeats itself to that line. Then we have 1, 2 again. So that's the type of equation we get. And we can, those delta y are calculated through the algorithm that we can implement. Then we determine the coefficients, and determining this coefficient we can recover the polynomial coefficients. Okay? That's how we implement the procedure. To solve for all the polynomials, all the cubic polynomials for the fitting. Okay, well, that's what we have for you in terms of what's the theory behind the fitting using cubic functions. There are other more complicated procedures that can be done, but let's do this, focus on the simple one. There are some built-in functions in MathCAD, some built-in spline functions. You have linear, quadratic, and cubic spline. We are focused on cubic spline because we want to work with the two-dimensional splines. We want to be able to use the previous results when we solved the numerical solution for the Laplace equation, have a numerical result. We want to fit that into a two-dimensional function, as explained in this workshop. There are two functions that are used to do cubic interpolation MathCAD. First one is C-spline. Which has two arguments. The first argument, I mean, this is for functions, one variable functions, single variable functions. X data is the X values in a single vector. Y data are the corresponding Y values. And this C-spline function returns a VS vector, which is used in the interpolation, in the final step in the interpolation, which is done using this built-in function interp. Interp has four arguments. The first argument is the one that is returned by this statement here. The second argument is the X values organized in the single vector. The other argument is Y values into a single Y data value, Y data vector. And this is the value of the function at the point X. So you can make a function, okay, a continuous function, with first and second derivatives that are continuous in the interior points. And this function can be written in this statement here, interp of Vs, which is calculated previously from data. We have to reinsert X and Y data here and calculate that interpolated value X. Okay. We also have, MathCAD also have two variable functions, splines. In this case, the syntax is something like this. C-spline is the first statement to calculate the final interpolation. It's C-spline. Now we have something called the XY data, which I'm going to explain in 1 second. And here are the Z values of the functions. For instance, this can be the potential function, the function of XY coordinates. How do you define this? XY data XY data contains all the X and Y values of your grid. Okay, so if you have a two-dimensional domain, suppose you have X values. Let's make it like this, X and Y. So we have a grid, equally spaced grid. Okay. So we have X from X0 to Xn, and Y goes from Y0 to Yn. So your X, Y data argument is simply a matrix of two columns. Here we have all the X values. Here we have all the Y values. So here, this point is X1, Y1. This point here is X1, Yn. Okay? This only tells MathCAD what are the values of X and Y, which are going to be used to calculate the Z values. Let me just show you a simple example here. to show how to call this function. Okay, just complete before we do that. So we have this is how you call the function. So we have xy data, the xy value in two column matrix xy data, and z data are the corresponding points, z coordinates, let's say, that could be a function of those two variables. So this is the same syntax of the one dimension. So use this vs to call a function interp, which is going to have a vs as the first argument, xy data, which are the x and y two column matrix, z data are the corresponding z values, and x is a vector in the plane. So x is xy transposed. So we call the function of two variables, okay, in this way. So we have an interpolation in two dimensions. I'm just showing you a quick example. Like this. I mean, this is an example. Just was playing around before. I made a data matrix, which is the sum of the square of the elements. So this is the matrix. Okay. In fact, my x value is the m variable. My y value is the n value of the variable. So n goes from 0 to 5, and then also goes from 0 to 5. So here is you see, I mean, this is, x is a vector, y is a vector, having the x values. So we have this vxy, as I told you, right? X values and y values. Okay. Here is a call to C-spline. M is the matrix, this is the z values, is right there. And then we make fx exactly as I showed before in my class note. Vs, vxy, m, and x. Just show you, I mean, if you want to calculate in a fraction, not integer value, at 1, 1, 2, 2, we have a value, interpolated value. Okay. For instance, I have f of xy defined as a function of two variables. Xy transposes the vector. I can calculate the derivative of f if I want. I mean, notice that once I have an interpolating function, I can calculate things, physical things. I can get the derivative and calculate. Okay. So this is the function itself. F, and I calculate the derivative here, which is a quadratic function has a plane as a derivative. Okay, so just to show how to use these things in MathCAD. Okay, well, continuing. Sorry. Just quit here. So coming back, we have this is the syntax of the built-in cubic spline function in 1 or 2 dimensions. So let's look at the workshop that we have to do. First part, we calculate the matrix equation I just showed before, equations 15, 16 of the notes. So do that paper and pencil or pen. Okay. Now, the question number 2 is to develop your own cubic spline. Okay. U is the set of data points. First column is the values of x, y is the values of y. And you're going to interpolate that in the x value. So this is a single variable function. So you do using that matrix equation. do some example in question 3. Mean a sine function. Let's do interpolation of sine function. Coarse grid. So let's see how the interpolated function looks like. You can plot also against the original sine function, see how it looks like. They are very close. So see how good is the approximation. Now, this is using your own function. Now do the same thing using the built-in spline function that we have in MathCAD. Compare the results, comments. Now, we're going to use the built-in 2D function, spline functions in MathCAD to interpolate the numerical solution of Laplace equation of workshop number 9, specifically those that you calculated in questions 2 and 3 of workshop number 9, okay? And after you do that, do some plotting, surface and contour plots for those splines, see how they look like. See if the contour plots look like the potentials that are expected to occur. And finally, the interesting question I want you to do is to now use the numerical solution of Laplace equation and the spline approximation for those numerical solutions to do field lines, okay? Because you have a continuous representation of the potential, you can try to make field lines using the prescriptions we gave before. Right, I mean, you can, field lines, you can calculate from previous signs that I gave you before. Now I have a continuous representation of the numerical solution of Laplace equation, and you can trace field lines. So do it and do some commenting on the results, okay? So that's what we have for this class. Till next time.